Well, hello, everybody. It's a great pleasure for me to actually be here because I usually attend these NCI Southwest MIRA workshops via Zoom. So one thing, I had no idea the room was so big and there were so many of you. I only ever see the speaker view. So I'm very pleased to be here and actually meet some of you in person again, and maybe for the first time. And it's also a great pleasure to welcome Dr. Alicia Magann. I've known Alicia for many years. She was one of our best students in the chemical engineering program at Arizona State University. She then moved on to Princeton, where she did her PhD. And she transitioned into this field that I think of as quantum computing. And unfortunately, I think all quantum computing is the same because I don't really understand it. So it's a pleasure to welcome her today, to have her give us her take on quantum control. Before I should say that, Alicia is also the recipient of the Truman Fellowship, right? So she's currently at Sandia National Labs in Albuquerque. So it's great to have her here today, and I'm looking forward to learning about quantum control. Alicia, thank you.
Thank you very much. Yeah, thanks for the nice intro, and thank you all for coming in person and on Zoom as well. So let's see, if I move around, I hope that people online will still be able to hear me. We'll see. So as Trevor mentioned in the introduction, my background is in chemical engineering, and the first experience that I had doing research, I worked on chemical engineering process control, where the things that we think about are taking a chemical process and tuning things like the temperature and the pressure in the chemical reactor in order to optimize some desired product that comes out. And I really enjoyed this. And then at some point along the way, I learned about something radically different, and that's the prospect. Oh no. That's the prospect of controlling chemistry with light. So the idea here is to use lasers in order to create tailored light that can coherently control chemical transformations in a way that wouldn't otherwise be possible through conventional chemistry and chemical engineering techniques. So here I have this little cartoon of a molecule. And so the premise here is that we want to take our laser and shine it on our molecule. So this little squiggle here is representing our laser light. And we want to tune this light so that it can speak to our molecule on its natural timescales. So think picoseconds or femtoseconds or maybe even attoseconds. We want to tune this laser light so that it can act as a photonic reagent and drive some desired transformation in our system. So there's lots of things that we could imagine controlling. One possibility is we might want to break a selected chemical bond such that as our molecule evolves under the influence of this laser pulse, we see this dissociation reaction happen. So of course, this is just one possibility. There's loads of other things that we might imagine doing using photonic reagents. So here's kind of a non-exhaustive list. So we can imagine rearranging molecules, orienting molecules, controlling isotope selective processes, controlling charge and energy transfer, and there's really many other possibilities as well. So this is a really big idea, but it's actually not a new idea. So the dream of using lasers to control matter through the light-matter interaction, these ideas date back to the invention of the very first laser in the year 1960. And so in the many decades since then, laser technology has advanced considerably, and we've been able to do proof of concept experiments. So we know that this works. We know that we can tailor laser light in order to drive desired dynamical transformations in quantum systems. And so just to tell you about a couple of the big ones, this was the first major demonstration of the principle of tailoring light. So this is referred to as quantum optimal control. It was published in 1998 in the journal Science. And in this paper, they looked at this organometallic complex, and they shined femtosecond laser pulses on it and showed that by tuning the shape of the pulse to have either this this shape over here, so this waveform, or this one over here, they could influence the product yields as shown by these little bar charts. So there have been a huge variety of other demonstrations that have been done, again, largely proof of principle in nature, and largely looking at controlling molecular systems in the gas phase. So to give you a little bit of variety, I wanted to show you just another example of an experiment that was done in the liquid phase. So this paper came out in 2005, and they looked at controlling isomerization in dye molecules that were dissolved in methanol. And they showed that by shaping the incident pulse, they were able to control the production of either the cis or the trans isomer of the dye molecules. So these are just two experiments. Over the years, there have also been continuous theoretical investigations. So I am a theorist and a computational scientist. And so I wanted to share with you some of the recent theory that people have done in this area. So one kind of cool paper is this one here, which was published in 2017, where the authors looked at designing laser pulses in order to make one system look spectrally like a different system. And so this generated kind of a lot of press. You can imagine making lead look like gold, and kind of fun things like that. And in their paper, they looked at, in particular, making hydrogen look like argon. So here is an unshaped laser pulse coming in. They simulate its interaction with argon. Argon emits this output optical response. And then they take this and they're able to design laser pulses that they can apply to other systems. So here's hydrogen in the ground state. Here's hydrogen in the first excited state. And here are the laser pulses that make the induced optical responses in hydrogen look identical to that of argon. Now, I know that this is a material science seminar. So after they looked at these atomic systems, they also considered material systems. So they looked at making conducting systems look like insulating systems look like conducting systems. And that again generated quite a bit of press, where the idea is that while the laser pulse is on, you can make a conductor look like an insulator and vice versa. But as soon as the pulse is off, it's back to being what it usually would be. And so that's what this video is meant to capture. Okay, so I've shown you that this is possible. We've shown this in experiments. There's lots of exciting theory that's been done to explore some of the possibilities in this area, but widespread adoption of quantum control and photonic reagents in real science and engineering applications just hasn't happened yet. And that's because designing photonic reagents, so designing laser pulses that actually do what we want them to do in systems that we care about, is hard. It's a hard problem. And so I now want to turn to some of the challenges that are kind of hindering progress in this area. So I'm going to go ahead and introduce just the general problem. So we want to design a laser pulse F. It's going to be time dependent. It's going to also depend on some parameters, these thetas. We want to design this pulse to steer some quantum system towards a desired control target. We pose this as an optimization problem. So we want to minimize a cost function, which is going to tell us how close we are to our target. And we want to find the laser parameters that get us as close as possible, so that minimize the cost function. Now, the way that we solve this optimization problem is we do it iteratively. So at each iteration, we evaluate our cost function. It tells us about our control performance. And then we update our parameters, test the next ones, and so on and so forth. So if I want to do this, if I have a system I'm interested in, and I want to design a photonic reagent, one way that I might imagine doing that is with an experiment. So this is a picture of one of the optical tables for my group at Princeton, where they do these types of experiments. And there's some challenges associated with exploring this in experiments, where the premise here is that the experiment you would actually apply the laser field, parameterized how you want it to your quantum system in the lab, and then you would evaluate your cost function by measuring your system. So that would tell you how well that you've done. You would pass the value of the cost function to some attached classical processor, which would update your laser parameters, and you would iterate and repeat this experiment over and over again until you finally iteratively found the laser pulse that does the control that you want. Now, unfortunately, doing these kinds of experiments is complicated. So these are highly complicated setups. And often if you want to look at a new quantum control problem, it can take years to get these setups built and get them working to actually do that experiment. And so if we want to get a complete picture of quantum control and all the different applications it could have and how it works, doing that through experiments alone is not going to be feasible. We really need theoretical support to help guide that. So the next possibility is, okay, well, maybe I can just simulate this. I can use a computer instead of going to the lab and doing everything in an experiment. So if I wanted to use a computer, then at each iteration, I would just simulate the dynamics of my quantum system that are induced by this laser pulse and calculate the resultant cost function. Now, unfortunately, this is also not very feasible. And the reason is that simulating the quantum dynamics of quantum systems is a notoriously challenging problem. And that's because the computer memory and the computer runtime that we need to do quantum dynamics simulations scale exponentially in the number of degrees of freedom that we have. And so this exponential scaling is a tremendous bottleneck. It's called the curse of dimensionality, and it really limits the systems that we can treat quantum mechanically on a computer and study. So we're often limited to just a few or a handful of atoms, sometimes even less, depending on the level of theory that we're applying. And so this really limits the complexity of the simulations that we can do. It means that we often can't study the most interesting problems on the computer. And so this is a real bottleneck in the field of quantum control. All right, so this is also not new news. So people have been aware of the fact that quantum dynamics simulations are difficult for a long time. And one person who is intimately familiar with this challenge was Richard Feynman. So he's famously quoted as saying that nature isn't classical. And so if you want to make a simulation of nature, you'd better make it quantum mechanical. And so Feynman went on to be somewhat of a visionary, imagining that we might be able to use a quantum mechanical computer, a quantum computer, in order to simulate quantum mechanical systems. And so he laid the groundwork, he kind of inspired this idea, and it is true. So this challenge that I told you about, this curse of dimensionality, is not present on a quantum computer. And so for the rest of this talk, I'm going to explore how we can put a quantum computer in the loop and use that to do simulations of quantum control. All right, so I'm going to start the rest of my talk by first saying a little bit about quantum computing, how it works, where the field is currently at. And then I'll dive in a little bit into a hybrid quantum classical algorithm for doing quantum control calculations that leverages the power of quantum computing in order to remove this curse of dimensionality bottleneck. I'll share some numerical illustrations, including looking at controlling state preparation in a model for a portion of the FMO complex, and how feasible it would be to actually implement this on a real quantum computer in the near term. And then I'll sum up and give a little bit of an outlook. All right, so I'm going to start off by giving just some nuts and bolts of quantum computing. So first of all, classical computing. So the computers that we all use are based on the premise of storing information in bits. The bits can be 0 or 1, and then we do logical operations on these bits. So a quantum computer is not so different. The only difference is that we're going to store the bits in the state of a quantum object, which we're going to call a quantum bit or a qubit. Then if I want to do a quantum computation, the nuts and bolts of that are given by these 3 stages. So the first step of a quantum computation is initialization. So I need to prepare my qubits in some specified initial state. So here I have these 3 arrows, And this is how we often visualize qubits. So an arrow pointing up represents 0, an arrow pointing down represents 1. So here we're just initializing the qubits in the string 0, 0, 0. The next step is to do the computation. So we apply a sequence of logic gates to our qubits in order to carry out some algorithm. And this is the quantum piece of our computation. So these are quantum logic gates. This here is a quantum circuit diagram. So this is how we reason about quantum computation, where the wires represent qubits, the blocks represent quantum logic gates, and then you move from left to right. At the culmination of our circuit, we need to be able to figure out the answer, so the result of our computation. And so this involves measuring the qubits. And so here, it looks like our quantum circuit has flipped the middle bit, and so the answer is the string 0, 1, 0. And so this is the general premise. This is how quantum computations work. These are the different pieces. And so to say a little bit more, the qubits are quantum mechanical objects, so they can possess unique properties. So if we have a pair of qubits, we might imagine preparing them in the state 0, 0, where they're representing the 0, 0 string, or we could prepare them in the state 1, 1. But because they're quantum mechanical, we can also prepare them in a superposition of these two states. And so this would represent an entangled state. We cannot separate the state of the first qubit from the second qubit. And we see that it's literally a superposition. And so these are features that we can achieve with a classical computer. And because we have these unique features, that directly affects our ability to do computations and the power of the computations that we can do. And so landmark papers from the 1990s looked at this and showed that there is a quantum speedup. So a speedup that a quantum computer would offer over the best classical computer for problems like factoring numbers, simulating quantum systems, and searching unstructured databases. These landmark algorithms led to, over time, worldwide engagement in developing quantum computing capabilities that would be able to implement these landmark algorithms and do things like factor numbers and simulate quantum systems. And so right now, things are very exciting. So there's a lot of momentum in the field of quantum computing today. So I think every week you get headlines about quantum computing being like the space race. And indeed, progress has been rapid. So one of the big milestones that people tend to be familiar with happened in 2019 when the team at Google reported that they had achieved this milestone called quantum supremacy. And this was an important moment. So they showed that they could use one of their prototype quantum computers in order to carry out a computation that wouldn't be tractable otherwise on a classical computer. And what they did is they sampled from a probability distribution. It took them 200 seconds. They argued that it would take 10,000 years on the best supercomputer. There was some debate, but I think it's agreed that it would at least take orders of magnitude longer on the best supercomputer compared with 200 seconds. So this was very exciting, but the problem that they looked at was contrived for the demonstration. So it wasn't a particularly useful problem towards any practical applications. And so today we're trying to move towards the moment where we can use these early prototype quantum computers like the ones at Google and other companies in order to do useful things and surpass classical capabilities towards applications that have real value. And now the time that we're in is often referred to as the noisy intermediate scale quantum, or NISQ era. And that's because we have these different prototype quantum machines. There's new ones coming out all the time, but they're not perfect, so they're small. And they're noisy. They have a lot of errors that we don't fully understand. And so that does limit the scales of the computations that we could do. And it's led to a new class of algorithms altogether being developed. And that is the class of hybrid quantum classical algorithms, where because we're limited in what we can do with quantum computers, the premise is that we couple our quantum computer to a classical computer, we put them in a loop together, and we try to get the best out of the quantum computer that we can, and do the rest with the classical computer. And so that often looks something like this down here. So we have this loop. The quantum computer does something like evaluate a cost function, which we hope it can do more efficiently than a classical computer. So we hope that it will offer us advantages. And then the classical computer is used to update the parameters that the cost function depends on. All right, so that was kind of a little bit of a whirlwind tour through quantum computing. I now want to go ahead and talk about some of my work looking at how we can use quantum computers, in particular algorithms like this, so hybrid quantum classical algorithms, to help us do simulations of quantum control. All right, so here's a flow chart. There's kind of a lot going on, but it's exactly what I told you. So this flow chart describes one way that we might imagine using a hybrid quantum classical algorithm to design photonic reagents. The orange pieces should look familiar. So we have those 3 stages. And this is the quantum piece of the computation. This is what we're using our quantum processor to do. The blue pieces are everything that we're not using our quantum processor to do. So this is what we can do classically on our conventional computers. And then we wrap it up into this quantum classical optimization loop, where in particular, we're using our quantum processor to evaluate a cost function, and our classical computer to update our control parameters. So I want to go ahead and talk through the different pieces of this flow chart, starting up here. So regardless of whether I want to use a quantum computer or a conventional computer to design a photonic reagent, the first thing I need to do is define my quantum control problem. And this involves defining a model for my chemical system or my material system or my quantum system that I want to control, as well as a model for my laser pulse that's going to come and interact and hopefully control my quantum system. I then need to define a target, so the dynamics that I want to achieve in my system using my laser pulse. So here, this is just a cartoon, of course, but we might imagine taking a molecule like this and orienting it so that it points in the plus X direction like shown here. Once we've defined our target, we then need to define an objective function that quantifies how well our control target is achieved. And so for this very simple cartoon, that's going to depend on the angle describing the difference between where the molecule is pointing and where we want it to point. So after we've defined our problem, the next step is to translate this quantum control problem into a problem that is amenable to study on a quantum computer. And so this task is called qubit encoding. The idea is that we are mapping the state space of our quantum system to the state space of our qubits. And so it's this step that Feynman had the vision about. So he said, or he imagined that because the state space of multi-qubit systems is going to have this exponential scaling property by virtue of it being a quantum system, that there's going to be an efficient mapping here. And he also conjectured that, in addition to the mapping, we can also potentially simulate the dynamics of these systems efficiently too. And so the takeaway message is that Feynman is absolutely correct. So we can encode our model for our quantum system into qubits, and that doing so provides exponential savings in the memory that we need. And so if we have a system with m degrees of freedom, and just for simplicity, we want to represent each degree of freedom using d dimensions, d levels, d basis functions each, then on a classical computer, we would need on the order of d to the m bits just to represent the state of that system. Whereas on a quantum computer, we would need on the order of m log d qubits. And so this is an exponential compression of the amount of memory that we need. So this is extremely powerful. We're now able to encode our system, but now how do we simulate the laser-induced dynamics of the system after it's been encoded? So this brings us to our quantum step of our computation. So the first step here is to initialize our qubits in a state that encodes the initial condition of our quantum system under study. And then we want to carry out a computation that simulates evolving that system over time as it's driven by our laser pulse. And so this brings me to another big milestone, and that is this paper here, which came out in 1996 by Seth Lloyd, and the abstract is very short. This is the abstract. It says, Feynman's 1982 conjecture, so the one that I told you about, that quantum computers can be programmed to simulate any local quantum system is shown to be correct. And so this paper was a big advance. So Seth Lloyd wrote down an algorithm that could simulate the dynamics of quantum systems on a quantum computer in polynomial time. So it could do that efficiently, providing, again, this exponential advantage in runtime, in addition to the exponential advantage that I told you about when it comes to the memory. And so here's just a kind of a repetition of that. Now, the actual costs associated with using a quantum computer are going to depend on the details of the algorithm that you use to do that simulation. But in general, there are quite a few methods developed by this point that allow you to do that in a time that scales polynomially with the number of degrees of freedom that you're simulating. All right, and so part of this work that I did was coming up with a recipe to do that. So if I actually wanted to go to a quantum computer tomorrow and simulate quantum control, this figure here, this quantum circuit diagram, gives a recipe that I could use in order to do that. I probably shouldn't dive too much into the details, but the general goal of the computation is to simulate the impact of the quantum time evolution operator on our initial state. And so all that this diagram is showing is that we can decompose this over and over again into successively simpler circuits, ultimately ending up as something that's effectively like machine code for a quantum computer that I could then go take and code up. All right, so after our computation, we read out the value of our cost function, which tells us how well our laser pulse did in controlling our system by measuring our qubits. We pass that to our classical coprocessor. If we've converged, we output our results. So our parameterized laser pulse. If not, we iterate until we do converge. All right, and so as a part of this work, we looked at exploring this in the context of different simple quantum systems and simple quantum control problems. And so the first thing that we looked at is controlling the bond stretch in the diatomic molecule hydrogen fluoride. And so for this, we modeled hydrogen fluoride as a Morse oscillator, and we explored how we could use this hybrid quantum classical approach to design a photonic reagent that achieved a desired stretch of this HF bond. So this is a simple vibrational control problem. Another problem that we looked at is a rotational problem. So we looked at controlling the orientation of two dipole-dipole coupled carbonyl sulfide molecules shown here. And then the last illustration that we looked at is controlling the preparation of an excitation in a model for a portion of the Fenner-Matthews-Olsen, or the FMO complex of green sulfur bacteria. And so this is a light harvesting complex, which is one of the key elements of photosynthesis in green sulfur bacteria. All right, and so with some of the rest of my time, I want to tell you a little bit more about this, this last demonstration. And so what we're looking at here is this reduced model that I considered for the simulations. So the model contained two coupled chromophores shown here, where the second coupled chromophore was additionally coupled to a vibrational mode, modeled as being in a thermal state at room temperature. So this, these are just two chromophores out of 7 in the FMO complex, and we simulated driving them with a weak electric field And we wanted to prepare an excitation on this first chromophore with that field. Okay. And so we simulated using our hybrid quantum classical algorithm in order to explore this problem. And in particular, we simulated implementing this algorithm on an error-prone trapped ion quantum processor. And we wanted to understand how feasible would it be to actually study this on an ion trapped quantum computer. And if it's not feasible, how much better does the quantum computer have to be before it becomes feasible? And so we looked at the three different stages of the quantum algorithm, and we simulated each stage as being infected by errors. And here are some of our results. So we looked at a simple cost function. So we just had two parameters in our laser pulse. And we considered the case where we have, first of all, just an ideal quantum computer. So there's no error. Let's establish a baseline. How well can we do in general? And so this is shown by the orange curve. So the orange curve shows how we're able to minimize our cost function as a function of the optimization iteration as we go around and around in this loop. We then looked at the case of realistic error rates in current trapped ion quantum processors, and we got the red curve. And so what we see here is significantly different. So the red curve, almost nothing happens. We're not able to minimize noise, and errors are completely washing out the computation. This is essentially garbage where we're not able to move. Now the blue curve is us looking at optimistic circuit error rates. And so these were taken from a paper where we looked at projections of how trapped ion quantum processors are hopefully expected to improve in the near future. And so we see in the blue curve that we are able to do a much better job compared with the red curve. So we see that we're able to minimize, although we're not exactly recovering the orange curve, which represents the ideal case. And so now turning to this lower panel, this heat map, this is showing the trajectory of the optimization parameters in parameter space. So in each case, the parameters are initialized at this black plus sign, and the global optimum, or the best solution, is here at this white X. Now the ideal case takes this little trajectory through parameter space as we optimize, ultimately getting very close to the optimum here. The red curve, so the realistic case, does a much poorer job, and it actually goes in the wrong direction with respect to theta 1. So it's completely lost. The blue curve, it actually matches the ideal curve extremely closely in the beginning, and then it kind of isn't able to make it all the way there. And so this study is just one example of how we can, I guess, think about the value of this in the near term. So we were encouraged by the blue curve. So we hope that we'll be able to do some kind of a proof of concept implementations of this in the near future. But we do have a long way to go before we're able to actually simulate interesting quantum control problems, for example, involving the entire FMO complex at the scales that would really help us understand this system better. All right, and so thinking about scaling up, thinking about moving into the future, we also looked at the resources that we would need moving forward if we had an ideal quantum processor. And so looking first over here, we looked at the quantum computer size. If we just have an arbitrary number of coupled chromophores, where each chromophore is itself coupled to some number of vibrational modes. And the takeaway here is we see that the qubit count that we need is scaling linearly with respect to the number of degrees of freedom that we had. And so before I told you that we have this M log D scaling, so this linear scaling with respect to the number of degrees of freedom. And so we shouldn't be surprised to see that recovered here exactly. Now over here, this looks at the scaling of the quantum computer runtime if we use quantum simulation approaches based on product formulas. And so this plots, again, the runtime. Here, this is the circuit depth, which is a a proxy for runtime, as a function of the number of coupled chromophores in our model. And yes, we see what we expect. So this is a polynomial scaling with respect to the number of degrees of freedom. All right, so I'll go ahead and sum up. So I started by telling you about quantum control and the big ideas in this area. But I also told you about some of the challenges that we face, and in particular, the notorious challenge associated with doing quantum dynamics simulations that are so important for guiding this field and pushing it forward. And so, this is due to the curse of dimensionality and the fact that the complexity of the calculations scale exponentially with respect to the number of degrees of freedom of the systems under consideration. Now, this is not new. So Feynman recognized this in the 80s and imagined that quantum computers could be powerful tools for doing these types of simulations to simulate the behavior of quantum systems. And then in this talk, I told you about how, not only can we use quantum computers to help us simulate and understand the behavior of quantum systems, but we can also use them to help us determine how we can control that behavior. So not just understand it, but also actively manipulate it and control it. So to that end, I talked through a hybrid quantum classical algorithm that could be used to design optimal laser fields for doing quantum control. Now this is a very general approach where the quantum computer is used to simulate the quantum dynamics, and this can be done with a number of qubits that scales linearly in the number of degrees of freedom and a runtime that is polynomial in the number of degrees of freedom. I then talked a little bit about applications to controlling state preparation in a portion of the FMO complex and the feasibility of implementing this on real quantum computers in the near term. So at this point, in terms of outlook, it is difficult to estimate when quantum computers will be mature enough to carry out meaningful calculations at scale. So it's difficult to know when we're going to be able to turn to a quantum computer and do these kinds of calculations to do real science and to do new science. And just to kind of toss this in, it's true that improving the performance of the prototype quantum computers that we have today is a quantum control problem in and of itself. And of course, we don't have a quantum computer to solve that quantum control problem. So it is a little bit of a catch-22 there. But whenever we do get to the point where quantum computing technology it does mature, then quantum computers do promise to be really powerful tools for scientific discovery and especially for quantum simulation. All right, so that concludes my talk. I want to thank my my funding agencies. So this was supported by DOE Office of Science and by a graduate and postdoc fellowship. And of course, thank my collaborators at Sandia and at Princeton, Matthew Grace, Mohan Saravar, and Hirsch Rabbits. Thank you all for joining, and I would be happy to take any questions.
Thank you, Alicia, for a wonderful talk. I see a few hands raised in the audience, so I'll take questions. But first, I would like to say, as an engineer, we need to have machine codes to be able to program our microprocessors, right? So this is the first talk I've seen where we've gone from quantum computers to something that might generate a machine code. So for me, that's been very helpful to understand how we might actually get to that point where we could use these quantum computers. So I can see Ryan has a question here. If you want to say the question, maybe I'll repeat it.
Thank you so much for the talk. It was absolutely wonderful. I have a couple of questions. I'll stick with one for now. It has to do with error correction.
Sure.
So what impact, I'm curious what impact quantum error correction would have on some of your results for optimization. And I'd also be curious to know whether or not the advantages that we're talking about with going exponential to polynomial scaling and memory and runtime, if those persist, if you have to implement error correction.
So would you like to, why don't you repeat some of that?
Yeah, so the question is about quantum error correction and how some of my work and some of what I told you about connects with quantum error correction, whether we need quantum error correction, and if we do, how that might impact some of the things that I told you about in this talk. And so that's a good question. And so let me just go back to my flow chart. So when I talk about quantum algorithms and some of these landmark papers, so I told you about factoring, I told you about quantum simulation, searching unstructured databases, all of these are assuming that we have an ideal quantum computer. So these algorithms are not assuming that I have errors in my quantum processor. This is very idealized. If I have a quantum computer that behaves ideally, I can show that it offers real advantages for these applications. And so this paper here, which shows that we can simulate quantum dynamics in polynomial time, is the same way. So we're assuming that we have an ideal quantum computer. And to have an ideal quantum computer, we need to correct the errors. We can't have errors in there. And so these results kind of depend on having quantum error correction. And if we don't, which at the moment we don't have that in our prototype quantum computers, then that means that we're not able to implement these algorithms in an ideal way. We might not be able to trust what the algorithm outputs because it could be infected by errors. And so we saw that in this little demonstration that I did. And so in order to really do big things in quantum simulation and do big things in factoring and do big things in general with quantum computers, we are going to need error correction, and we are a long ways away from that. And so I think what a lot of people are doing today when we have noisy quantum processors is they're trying to explore, can we do something useful? They're trying to simulate it. They're trying to understand, is there a prospect for me to use this error-prone device to do something cool? And you do this by either testing it out on hardware or doing simulations. And so that's kind of what I did. But yeah, it's unfortunate, but it's a reality that we need quantum error correction to implement some of the more exciting quantum computing algorithms at the scales needed to be meaningful.
A question in the back of the audience, and we'll take one here.
Thank you for the talk. I wanted to ask you about, you're focusing mainly on trapped ion.
Yeah, that's a great question. So
Repeat the question.
the question is, why did I consider a trapped ion quantum processor, and what might I expect in other platforms besides trapped ions? And so the reason that I thought about a trapped ion quantum processor is because I'm at Sandia and we have a trapped ion quantum processor. We have a lot of expertise. We're excited about it, and so that's why I looked at that. Now, trapped ions are one of the leading platforms for building a quantum computer right now. And the other leading platform is probably superconducting qubits. So Google and IBM and some of the big players have superconducting qubits. This is what was used to do that quantum supremacy demonstration. And so I can't speculate about superconducting qubits. I haven't looked into what the projections are in that space, but it's a great question. And it would be interesting. I think that if I were to try to implement this on hardware, I would probably use IBM's hardware, and then I might learn something. But I'm interested myself to better understand some of the projections in superconducting qubits, how they compare with trapped ions, and it'll be interesting to see how things go.
So before we get to the question, I wanted to follow up with that, and maybe it's putting you on the spot a bit, but how optimistic does optimistic mean? Are you being super optimistic, or are you thinking,
It's a good question. So I think I chatted with one of the experimentalists at Sandia about the optimistic parameters, and she seemed to think that it was reasonable in the next few years. So the optimistic projections are based on reducing some of the motional heating in the trapped ion and reducing photon scattering. And she seemed to think, as the head of the experimental effort, that these were reasonable projections, and more I can't say.
Sure, but so not decades, but a few years.
Yes,
Yeah,
the hope
reasonable.
is in a few years.
So we have a question here. Yes, thank you.
Yes, thank you for your talk. Really interesting stuff. I was curious with these hybrid algorithms for classical computing. Will they be able to be translated into fully quantum algorithms when the technology gets caught up?
Yeah, that's a good question. So the question is about hybrid quantum classical algorithms and whether we can translate those into fully quantum algorithms in the future if we want to, if the quantum computing technology can handle that. And the answer is yes. So quantum computing is universal. So anything that we can do with a classical computer, we could do with an ideal quantum computer. So we can reverse between the two. Now there could be overheads. We might need extra qubits, or we might need more runtime, but we can translate anything back and forth in principle. And so if we have a hybrid quantum classical algorithm, sure, we could put the whole thing on a quantum computer, but it might not give us any advantage. We might be better off using a classical computer just due to the overhead associated with it. And so that's kind of the idea, where we're just going to use the quantum processor for the one thing that we know it's good at, and then just do the rest on the classical computer.
So Ryan, a question?
I was so intrigued by the photo radiation example that you showed us. I thought it was super interesting. Tell us a little bit more about the nonlinear optical processes that are at play there. What's behind some of the physics that you were showing?
Are you asking about the very beginning?
Example, the making a material that's not a metal that you like metal.
Oh, sure. I threw that in after I realized this was a material science seminar. So let's just go back to that. Here we go. So this is work that I think is really cool. So I collaborate with this group, but I wasn't a part of it. And so what they did is they looked at a simple model for a material. Again, it's hard to simulate these things, so we can't simulate very complex materials in a fully quantum way. So they looked at the Fermi-Hubbard model, and they looked at a 1D Fermi-Hubbard model. So I think they looked at 10 sites in one dimension, and then you can simulate the Fermi-Hubbard model as a conducting system or an insulating system by tuning the parameter. And so that's what they did. They looked at essentially a Fermi-Hubbard model that was conducting. They determined the current that was generated by applying an input field to their Fermi-Hubbard model. And then they took a model that was in a Mott insulating state, and showed that they could design input laser pulses that could produce exactly the same current, so that it looks like a conducting system while the pulse is on. Does that answer your question?
All right, I think there's one more question. Yeah.
I had a couple of questions, but my first one is maybe I didn't catch it, or maybe I didn't quite understand, but when you were talking about modeling the FMO complex, why is it that the degrees of freedom directly affects the chromophore ratio?
I'm sorry, can you repeat just the end of your question?
Why is it that the degrees of freedom that is present in the system affects the qubit to chromophore ratio that you're able to?
All right, so let me get to that. So the question is about the numerical illustration of the FMO complex, and you're asking about these resource projections. And so here in the model of the FMO complex, the degrees of freedom that are in this model, at least the way that I modeled it, are the chromophores and the vibrational modes. So those are my degrees of freedom, and the number of qubits that I need scales linearly with respect to both of those degrees of freedom. And so I plotted it with respect to the number of chromophores and considered coupling the chromophores to 1, 2, or 3 vibrational modes each Does that answer your question?
Yeah, kind of.
Okay, so the chromophores are the degrees of freedom in the calculations that I was looking at.
Sure, go ahead.
So I had a professor in my undergrad who worked with like protein folding and it ran into the same problem, like really complex, too many degrees of freedom. So his research was kind of like scaling that down to smaller kind of compartmentalized pieces. Is there any way that like that technique could be used in addition to this quantum computing? Because you're trying to do the same thing, like making runtime quicker. So is there any way that you can simplify your systems and kind of get rid of some of the parts?
Absolutely. So the question is whether we might benefit from simplifying our calculations or breaking them into pieces in order to make them easier to deal with. And I think that quantum computers will be powerful, but they're never going to be infinitely powerful. And so we're always, going to be looking for simplified models, right? We're not going to be able to simulate every atom in the universe using a quantum computer at the quantum level. Of course not. And if we have a protein, there's so many atoms in there. If we want to treat that quantum mechanically, even with the best quantum computer, we're going to need to make simplifying assumptions, make approximations, just treat parts of it, and so on and so forth. So it's not a quantum computer is not going to solve these problems. We're going to still need to consider model systems. The problem that it's going to solve is that it will be scalable, but there will still be some limit defined by either how many qubits we have or how long we want to wait for the answer.
And then, yeah, so, okay, yeah, in the middle here. Yeah.
Yeah. Yeah. So the FMO, this is a question about why we looked at the FMO complex. So the FMO complex is a very well-studied light harvesting complex. So people are really interested to understand energy flow in light harvesting complexes. People look at FMO a lot in order to do that, understand if there are quantum processes at play and how these systems behave. And so that's why we looked at the FMO complex because of the relation to energy flow. And the problem that we looked at is creating this excitation on one of the chromophores, because if we had this system in the laboratory and we were able to create this localized excitation, that could be really helpful for us to then study how that excitation gets dispersed using spectroscopy in the lab. And so the quantum control is to sort of help us artificially mimic what the sun would do in this system.
So maybe time for one last question from Garrett here.
What do you talk?
Yes.
It's only because you're talking really interesting. So I'm really intrigued by this idea of the photonic reagent and the diversity of problems. I'm curious if after you go through this whole iteration, you find the appropriate photonic reagent to achieve whatever goal you're interested in. What do you learn from that photonic reagent itself? What does that teach you about the starting system and trying to achieve the goal?
Yeah, so the question is about photonic reagents. So after we compute them, what can we learn from them? What can we learn about the physics of the system or the mechanism? And that's difficult. Some of the experiments that I showed, these are heroic experiments. We're able to show that we can control quantum processes using lasers. But what we can't do is understand what the laser is actually doing to achieve that control. And that's partially because we can't simulate what's happening. So we don't have that theory support. We can do the experiment, we can record, okay, we're able to increase this product, but we don't know how. We don't know what the mechanism is. We didn't learn anything about the physics except that we've been able to do what we wanted to do. And so that's actually one of the things that I was interested in doing when I started my PhD. I wanted to do this theory support to support the experiments in our group at Princeton, but it's just too hard. And ultimately that led me to quantum computing as a potential path for doing that theory support in the future. And so I think that just computing a photonic reagent on its own, it's probably hard to learn something from the shape of the waveform. But you might be able to learn something either through simulation support, through spectroscopy maybe, and this sort of thing.
Well, maybe we should wrap up there. Thank you all for coming. Maybe we could thank our speaker one last time. Thank you, Alicia. So my guest, Garrett, you'll stop recording. And do you want, are you able to